So, last time we saw Cauchy integral formula, and I will repeat this statement again for the ready reference, because that is one of the important formulae that we want to apply in future for solving some problems and proving some more results. So, the statement is let f be analytic on and inside a simple closed contour C and Z0 be point in the interior of C. Then yes, fz0 is equal to 1 upon 2 pi I integral over C fz upon z minus z0 dz. So, this is Cauchy integral formula. So, the picture to be stored in mind is this form. So, this is C and Z0 is point here and f is function which is analytic on this contour and everywhere inside. Okay. Then fz0 can be found by using this formula, and since z0 is any point, we can apply this formula actually to any general point z. Okay. So, we can have f dash z is equal to 1 upon 2 pi I integral over C. Now, variable over C you can replace by s suppose. So, fs upon s minus z ds. So, this actually is the function f dash, all right. So, this is function f dash is expressed in the integral form. So, f is analytic, so of course f dash exists for every point z, but f dash is given by this, that is important. Not only f dash, last time we also saw that if you consider f dash z plus delta z minus f dash z upon delta z and take limit as delta z tends to 0, then you get a formula for f double dash. You get a formula for f double dash in terms of integral. So, f double dash z is 1 upon 2 pi I, 1 upon pi I integral over C fs upon s minus z whole square ds. So, this is formula for f double dash z. Okay. This formula proves that f dash is also analytic. Okay. So, that was most important consequence of the Cauchy integral formula, that if f is analytic, then so is f dash. So, this formula is valid for every point z inside this. So, in particular you may apply to a certain point z0. So, suppose f is analytic at z0, there will be neighborhood such that f is analytic at every point in this neighborhood, and then as a particular case of this you can say that in this neighborhood f dash is analytic, f double dash is analytic, and so on. So, f dash, f double dash all will be analytic at point z0. That means they will be analytic in the open neighborhood of z0. Okay. So, important corollary that we saw last time was if f is analytic at z0, then f nth derivative at z is also analytic at z naught, is analytic at z naught. For all n natural numbers, that is, or you may say integers, all n equal to 0, 1, 2, non-negative integers. So f is analytic, f dash is analytic, and so on. So this is very crucial and important. This will lead to power series expansion of f around z naught. So if the function is analytic at z naught, this corollary states that all the derivatives of f exist at point z naught. Not only that, nth derivative function is analytic at z naught, and this will in turn help us in writing Taylor series expansion of function f around z naught, which we will definitely going to see. But before that, let us see the formula for the nth derivative. That also we stated last time. So just like we have this formula for f dash, f double dash, nth derivative is n factorial upon 2 pi I integral over c fs upon s minus z to the power n plus 1 ds. So this is general formula which you can apply for any n. Okay. This is the general formula which is applicable for function f, which is analytic on and inside a simple closed contour C, and z is any point to the interior of C. That is the situation. Then all these formulae are applicable. See, these are formulae for every n. This is the formula, and all of them are applicable in the situation. See this situation, that f should be analytic on and inside C, and z should be point inside C. Then you can always write down these derivatives in terms of integrals. Okay. Now with this, let's do some problems. Okay. So maybe examples. Examples is suppose you want to find out this integral. So some curve C is given to you. So C is given by, suppose curve C is boundary of a rectangle, given by x plus or minus 2, given by x equal to plus or minus 2 and y is equal to plus or minus 2. That means this is 1, 2, minus 1, minus 2, 1, 2, minus 1, minus 2. So you may have this rectangle. So this is boundary C. So this is our curve under consideration. Okay. So this is simple closed contour. Remember that this is not a differentiable function at this point. So this is not a smooth curve, but this is piecewise smooth. So this is a contour and this is a simple closed contour. Okay. Now we have to apply Cauchy integral formula for this contour. So let us see what is function under consideration. That is, so evaluate the integral, integral over C e raised to minus z dz, upon z minus I pi by 2. Now see that this is typically of the form fz upon z minus z naught. So we should immediately recognize that this evaluation of this integral is application of the Cauchy integral formula. Do you understand? This is fz upon z minus z naught. See this formula again. Integral fz upon z minus z naught. Okay. So it is exactly of this form, this integral. Alright, this integral is exactly of this form. We compare these two maybe. Alright. So now we just see whether the conditions of the Cauchy integral formula are satisfied. What are conditions? So I will call this as fz. So fz is e to the power minus z. So that this is fz upon z minus z naught. What is z naught? Z naught is I pi by 2. This should look like fz upon z minus z naught. So z naught is this. Now conditions for the Cauchy integral formula to hold are f should be analytic on and inside C. This is our curve C. So this is plus 2, minus 2, plus 2, minus 2. Where is I pi by 2? I pi by 2 is somewhere here. Okay, I pi by 2 is somewhere here. So it is inside this. I pi by 2 mod, or this will lie on y axis with value pi by 2 is less than 2. So it will be inside this circle. So let us write z naught is inside C. C is our given curve. So z naught is inside C. And what about f? F is analytic everywhere. F is entire function. F is entire. So it is analytic on and inside C also. It is analytic everywhere. So analytic on and inside C. So the conditions of the Cauchy integral formula hold. And once the conditions of the Cauchy integral formula hold, what will happen? That integral fz dz upon z minus z naught is 2 pi I times fz naught. So see this. Now you can evaluate this integral as, so now we have, so this integral e to the power minus z upon z minus I pi by 2 dz over C is equal to this 2 pi I will, because here we have only integral. So 2 pi I times fz naught. 2 pi I times fz naught. Now just see what is f. F was e to the power minus z. So 2 pi I times e to the power minus z naught. But what is z naught? 2 pi I times e to the power, z naught is I pi by 2. So minus I pi by 2. What is e raised to minus I pi by 2? It is cos of minus pi by 2 minus I sin pi by 2. Cos pi by 2 is 0 and minus sin pi by 2 is minus I. Okay. So this is equal to 2 pi I times cos pi by 2 minus I sin pi by 2. Sin pi by 2 is 1. So this is minus I. Minus I into plus I is minus I square, that is plus 1. So this is 2 pi. So value of the integral is 2 pi. So remember, this we have not solved by just the definition, that is f of zt into z dash t dt or anything like that. Looking at the form, it is clear that it is application of the Cauchy integral formula, that is fz upon z minus z naught. Only thing we have to identify what is f, what is Z naught, and check whether Z naught is inside C and F is analytic on and inside C. Then it is applicable. So this integral is then 2 pi I f Z naught. Then we just substitute. Okay. Let's go to another problem, similar problem, because you understand the formula better if you apply and understand how to apply this in different situations. Okay. So next is integral over C. Now the curve C is same, that rectangle, plus or minus 2, plus or minus 2. Now you want to evaluate, so evaluate integral over C cos Z upon Z into Z square plus 8 dz. Cos Z upon Z into Z square plus 8 dz. Okay. Now you look at the denominator. Look at the denominator. Denominator is Z into Z square plus 8. So what are points where this function is not analytic or where the denominator is 0? Of course, for Z equal to 0, it is 0. And at point Z square equal to minus 8. So denominator vanishes at points Z equal to 0 and this Z square equal to minus 8 you want to solve. That means Z is equal to I into 2 root 2. I into 2 root 2. You may have plus or minus. Plus minus I into 2 root 2. So Z square is minus 8, means you will get these roots. So this I into 2 root 2, this absolute value is bigger than 2. So it will go outside that rectangle. Do you understand this? So these points I 2 root 2 and minus I 2 root 2 are outside the rectangle whose boundaries are x equal to plus or minus 2, y is equal to plus or minus 2. So these points are outside the rectangle. So if I consider now the function fz as, yes, can you suggest? So looking at this, we want it in the form fz upon z minus z naught. So I will take fz to be, so let fz is cos z upon z square plus 8. Why can I do that? Because the points where this function is not analytic are outside our contour C. Okay, so this is analytic. So let me write this in this first problem explicitly. See, f is not analytic, so you may take down this. F is not analytic at points z equal to plus or minus I into 2 root 2. Thus, f is analytic on and inside the given contour C. Is this clear? Because these points are outside the contour. So this function is analytic on and inside C. That is the requirement for applying Cauchy integral formula. So we can apply Cauchy integral formula to this function. Though this is not entire function. It is not analytic everywhere. But the points where it is not analytic are outside our contour C. That is the whole point. And for applying Cauchy integral formula we need what? F is analytic on and inside C, which is satisfied. Now what is the other factor here? It is Z, that is Z minus 0. Okay. So I will take Z naught equal to 0. So let Z naught equal to 0. Then this Z naught is inside C. Z naught is inside C. So both the conditions are satisfied. That is, this Z naught is inside C and F is analytic on and inside C. So by Cauchy integral formula, this integral will be equal to 2 pi I times Fz naught. That is 2 pi I times, now what was F? F was this. So you put Z naught equal to 0. So cos 0, that is 1 upon 8. Cos 0 is 1 and then this is 0, this is 8. So you get Fz naught to be equal to 1 by 8. So that is pi I by 4. See this again. Looking at this integral, we understand that it is application of Cauchy integral formula. Now point is, what should be F and what should be Z naught. Now we know the curve C. So F should be that function which is analytic on and inside C. So cos Z upon Z square plus 8 satisfies that condition, because roots of Z square plus 8 are outside C, and this Z equal to 0, this factor is like Z minus Z naught, this is Fz, so this is Fz upon Z minus Z naught, that is 2 pi I times Fz naught. With this Z naught satisfies the condition of the theorem that it is inside C. So, and then you just plug in Z naught in F. Cos 0 is 1, 0, 1 by 8. Clear? Let's do one more problem. Find the value of the integral of gz around the circle mod z minus I equal to 2. Okay, let me write. Find the integral of gz around the circle mod z minus I equal to 2. Integral of gz or C, where this C is mod z minus I equal to 2. Where, what is gz? Where first gz equal to one upon z square plus 4. Now you want to try this. Shall I give you 2 minutes? See, this is integral 1 upon z square plus 4 dz over this you want to find out. So can you apply Cauchy integral formula? Just check which f you will take, which z naught you want to take, and then how do you apply the Cauchy integral formula. I will give you 2 minutes. So this is the problem. So focus on this. First of all, try to draw this curve mod z minus I equal to 2. This is circle with center at I and radius 2. Okay, so draw this and then check what z naught you will take. what are points where g is not analytic? So you have to factorize the polynomial in the denominator. You have to factorize on the polynomial on the denominator. Okay? So try to factorize the polynomial in the denominator, that is z square plus 4. So what are roots? Z square equal to minus 4, so z is plus or minus 2i. So this g is not analytic at z equal to plus or minus 2i. What is contour C? Have you drawn? So let me draw the contour C. Okay, let me draw a bigger picture maybe. I will draw it here. So this is I, so this is 0, this is I plus whatever, this is I 2i, 3i. So this radius is 2. This center this, so it will be circle of this type maybe. This is center. I have drawn a rough picture anyways. And what are points where it is not analytic? It's plus or minus 2i. Okay. So this minus 2i is here because this will go up to minus I. But this plus 2i is here. Minus 2i is here. And then this is center of the circle. This is 3i because radius is 2. This is 0, this is 1. So this is I. This is minus I. Minus 2i. So minus 2i is outside. Okay. So this gz I will write now as, yes, can you tell me? It is 1 upon z plus 2i into z minus 2i. Z plus 2i into z minus 2i. Now this factor 1 upon z plus 2i, okay, I can take as, say suppose fz is 1 upon z plus 2i. This denominator is 0 at minus 2i, but that minus 2i is outside the given curve. So this function is analytic on and inside C. So f is analytic on and inside C. Okay. Now what is Z naught? Z naught is, yes, Z naught is point inside C, that is plus 2i. Because see, this plus 2i is inside C. Okay. So this is Z naught, this is f, and now you have integral fz upon z minus z naught. So Z naught is 2i, so Z naught is inside C. So integral gz dz over C can be written as integral fz upon z minus z naught, because this z minus z naught is z minus 2i, fz is 1 upon z plus 2i, so that is given function 1 upon z square plus 4. Okay. Now this is equal to 2 pi I times fz naught. Pi I times fz naught. Now your fz is z plus 2i. Okay. You put 2i in this. So 2i plus 2i is 4i. Okay. So this is fz naught is 4i. So this is 2 pi I times two I plus 2I is 4I. It is 1 upon z plus 2I. So 1 upon 4I. That is, this is equal to pi by 2. So value of the integral is pi by 2. Next problem is evaluate z square plus 4 bracket square. Evaluate integral 1 upon z square plus 4 bracket square dz over C, where C is this contour, where C is this contour. Okay. Center at I and radius 2. So 2I is point inside and minus 2I is point outside. Like that we have taken the function. So now here, alright, so this is bracket square here. So this will be what? So this bracket square means, you see this formula now. Do you see this formula? This bracket square means this is n is 1. So n is 1 means it is f dash z. So if you have point z chosen inside C, then you will find out f dash z naught. So now we will apply the formula for f dash. Okay. So z naught is 2I and fz is 1 upon z plus 2I, because this is analytic, because minus 2I is outside. Okay. What is f dash z? What is f dash z? Derivative of 1 upon z plus 2I is what? Minus 1 upon z plus 2I whole square. This is derivative of f. This is f. So this is f dash. Okay. And this integral is nothing but, okay, integral 1 upon z minus 2I whole square into z plus 2I whole square. Okay. So we need to take fz equal to 1 upon z plus 2I whole square. Okay. So we have to be careful, because this should look like fz upon z minus z naught whole square. Okay. So this fz is 1 upon z plus 2I whole square. This z equal to minus 2I is a problem point which is outside C. Okay. So now this is, so this derivative is, we have to change. So it is minus 2 bracket cube. Is this clear? 1 upon z plus 2I bracket square, derivative is minus 2 upon z plus 2I cube. So this is now of the form integral over C fz upon z minus z naught bracket square dz. This is pi I times f dash z naught, because this formula which I showed you just now for the nth derivative, substituting n equal to 1 here, okay, and then here it is n plus 1, so you get 2, and then n factorial upon 2 pi I, okay, so you get 1 upon pi I times f dash z naught. Okay. Now here it will be 2 pi I, because in f dash z naught you get first derivative. Let's check this formula again. This n equal to 1, then you will get n equal to 1 here. So you will get 1 upon 2 pi I. So 2 pi I times this. Okay. So 2 pi I times f dash z naught. Alright. So now we will apply it. Now this is f dash z, you put z naught, that is 2i. So 2i plus 2i, that is 4i bracket cube. So 2 pi I times minus 1 upon 4i minus 2 upon 4i whole cube. Because z is 2i, z naught is 2i here. So f dash z naught is 2i plus 2i 4i. And I cube is minus I. Okay. So this will be minus I, so this will be plus I. So I will get cancelled. Okay. So you simplify this and whatever is the answer. Okay. So this is 4 pi, I cube is minus I, this plus I will get cancelled upon 4 cube. Okay, 64. So this is pi by 16. Pi by 16. Clear? Next problem. Let C be the circle mod z equal to 3. Okay. Next problem is, let C be the circle mod z equal to 3. That means circle with center at origin radius 3. Circle with center at origin radius 3. Show that if GW equal to, show that GW equal to 2z square minus z minus 2. GW equal to integral over C 2z square minus z minus 2 upon z minus w dz. Z minus w dz, where mod w is not equal to 3. That means this point w is not on the circle, otherwise this z is on the circle and it will become 0. So w is not on this circle. Okay. So this is GW, this is definition of GW. Can you see this? I will read it. GW equal to integral over C 2z square minus z minus 2 upon z minus w. Okay. Now what we need to find out? So evaluate. So find G of 2. So it is asked that show that G of 2 8 pi I. G of 2 is 8 pi I. What is G of 2? You put W equal to 2. So G of 2 is integral 2z square minus z minus 2 upon z minus 2. You just plug in W equal to 2 in the formula for G. So by given this thing, expression for G, this expression for G, you want to find G of 2. So you put W equal to 2. That is integral over C 2z square minus z minus 2 upon z minus 2 dz. But this is typically of the form fz upon z minus z naught, where this z naught must lie inside C. But what is C? Circle with center at origin radius 3. So it is like this. So this is 3. So this is 1, 2, 3, 1, 2, 3. And this point 2 is here. This point 2 is here. That is 2I. This is 2 is here. This point. So this is inside C. And fz I can take this so that it will become fz upon z minus z naught. So our fz is 2z square minus z minus 2. And this is z naught. So fz upon z minus z naught is what? 2 pi I times G2. Okay. So this integral is 2 pi I times F2, Fz naught. This is F. So this given integral, that is G of 2, is 2 pi I times Fz naught, where this is F and Z naught is 2. So put Z equal to 2. So 4 into 2, 8 minus 2, 6 minus 2, 4. So this is 4. So 4 into 2 pi I. So 8 pi I. That is what we wanted to show. This is very simple application of the Cauchy integral formula. That is, you want to find G of 2. Okay. The next question here is that what is value of GW when mod W is bigger than 3? So what is value of GW what is value of GW? GW when mod W is bigger than 3. Now when mod W is bigger than 3, if you look at this curve, this contour, this is mod W equal to 3. Now if this W, so our G is this function. So 2z square minus z minus 2, let me write again this G. So GW is integral over C 2z square minus z minus 2 upon z minus W dz. Now if W is the only point where this function, this quotient is not analytic. So this total fraction is not analytic at z equal to W. Okay. But if mod W is bigger than 3, this W will go outside this circle over which we are integrating. So if mod W is bigger than 3, this entire function, that is this fraction, then 2z square minus z minus 2 upon z minus W is analytic on and inside C. Because this is not analytic at W. But where is W? W has absolute value bigger than 3. So W will go outside this circle. So inside this entire fraction is analytic. This function is analytic. Do you understand this? And if a function is analytic on and inside C and C is simple closed curve, then what is value of the integral? That is our first version of the Cauchy theorem. Do you remember that? That is, if f is analytic, so now this is my f. So if f is analytic on and inside C and C is a closed curve, then integral of f over C is 0. Okay. So now by Cauchy theorem, integral over C 2z square minus z minus 2 upon z minus w dz is 0 if mod w is bigger than 3. So the integral will be 0. Okay. The next problem asks that now in this problem this C was mod z equal to 3. Okay. But in general, if you take any simple closed contour C, so suppose if you consider the similar problem here, that is if you consider GW, so suppose next problem is like this, GW equal to, so GW equal to integral over C z cube plus 2z upon z minus 2 whole cube, z cube plus 2z upon z minus w whole cube dz. So this is your integral to be evaluated, but it will depend on different values of w. So for what w, what will be value of gw? So this C is not described yet. So let us see what is C. C is actually any simple closed contour in the plane. Now C is any simple closed contour. Okay. Now there are two cases, of course, and W is such that W is not on C. If W is inside C, what is value of GW? And if W is outside C, what is value of GW? Which is simple. Suppose if I ask you the question that there are now two cases, that W is inside C, W is outside C because W is not on C, that is given suppose. And this C is any simple closed curve like this. Okay. So this is curve C. And this is GW. It is defined for all points W except for the points on the plane. W is not on the curve C. Except for the points on the curve C, everywhere G is defined. What will be value of W if W is inside this curve? And what will be value if W is outside the curve? That is what we want to find out. Okay. Is this clear to you? Now which case is simpler? If W is outside, can you immediately tell me what will be value of this integral? If W is outside this, look at the denominator. Denominator becomes 0 only at Z equal to W. So this function is not analytic at Z equal to W. But if W is outside C, this function is analytic on and inside C. What we need is on and inside C. So on and inside C, this function will be analytic if W lies outside C. And then this is a simple closed curve and the function is analytic, then integral will become 0. Then by Cauchy theorem, integral will become 0. Is this clear? That this is simple closed curve, this is W suppose, then in that case Z minus W is analytic. It is not analytic at W, that is fine. But why do we bother? Because we want to integrate on this and the function is analytic here and also on this. Okay. So the function Z square plus 2Z, so Fz equal to Z square plus 2Z upon Z minus W whole cube is analytic on and inside C if W lies outside C. And in this case then, in this case, integral over C will be 0, Z square whatever that is given upon Z minus W whole cube dz is 0. In that case it will be 0 because the function is analytic on and inside C. C is a simple closed curve. So this is 0 by Cauchy's theorem. By Cauchy theorem. Now if W is inside C, W is inside C, then we need to apply this formula. Because this Z is inside C and S minus Z raised to n plus 1. Here we have Z minus W bracket cube. That means you want to find second derivative. Second derivative you want to find out. Now look at this function. Z square plus 2Z upon Z minus 2Z. So this is your, whatever you may call this as function F now. In the next problem, this problem is over, so I will use the same symbol F, but now F will change. So look at this problem, okay, this problem. So we have done the case when W is outside. Now consider the case when W is inside. W is inside C, okay. So I will write it here again, okay, so that you can see the curve also. So suppose W is inside C, then this is typically of the form point is inside C and Fz upon Z minus Z naught whole cube, okay. So now let Fz equal to, you only take now Z cube plus 2Z. Now you just take Z cube plus 2Z, okay. And then integral is of the form what? So GW now becomes integral over C Fz upon Z minus W dz whole cube. Now you again see that formula now. You see the formula. Nth derivative at a point which is inside C is n factorial upon 2 pi I Fs upon s minus z raised to n plus 1. Here we have 3, so n must be 2. So we need to apply the formula for second derivative. Okay. So by, okay, and then second derivative into 2 pi I upon factorial n is integral, because we want to evaluate this integral. Look at this formula again. We want to evaluate the integral. So it will be 2 pi I nth derivative upon n factorial. Is this clear? So this is 2 pi I upon n factorial, that is 2 factorial. Okay, because n equal to 2 we have to take. N equal to 2 we have to take. So 2 factorial into second derivative of f at point w. Second derivative of f at point w. Is this clear? So this is 2 pi I upon 2, so this is pi I, and this is f. So what is second derivative? First derivative is 3z square plus 2 and second derivative is 6z. So 6z evaluated at w, that is 6w. Okay. So now this GW becomes 6 pi IW. Okay. So value of GW in two different cases we have found. In the first case, when W is outside, GW is 0. If W is inside, GW becomes this. And then typically it is application of the Cauchy integral formula, because W is inside and the function f chosen which would suit the given integral to become in the form fz upon z minus z naught whole raised to some power. So this power is 3, and then we have to use formula for the second derivative because of this. Okay. So that is how one deals with the problems on Cauchy integral formula and the derivatives of the function f, the higher order derivatives of f. So higher order derivatives of f are used to evaluate the integrals in this manner. See, here we have found the value of second derivative of w. To evaluate this integral, this at point w. See, you may choose now any point w inside C. So suppose some specific curve is given, we may choose point inside C, and then we get value GW. Okay. So the important point in this entire theory is that if you have a function analytic on and inside a closed curve C, value of the integral is 0. Understood? So the function f that we are going to integrate is suppose analytic on and inside that contour, then integral is 0. That we have seen long back when you were here in Pratishthan. I told you this theorem. When point z0 is inside C, then you can find fz upon z minus z0 integral by using Cauchy integral formula. So fz0 is fz upon z minus z0, and then you can find f dash z, f double dash z, and f nth derivative for any n, and the formula is this. So this is most important formula that we are applying for different values of n. If n is 0, it is just fz which can be written, which we are using for fz0. So here z0, same formula. When n is 1, then we are writing f dash z and so on. So looking at this power, we come to know which formula we want to do. So when you want to evaluate integral, and if it looks like this for some value of n, then you have to appropriately choose f and z0 which lies inside this, and f should be analytic on and inside C. Then you will immediately get by Cauchy integral formula and its higher order derivatives. So as you must be observing that Cauchy integral formula is the crux of the matter. That is the actually the formula which gives rise to many important results in one variable complex analysis. Okay. So, we will continue and see some more applications of Cauchy integral formula